Okay,
Okay, go ahead.
so welcome to GADEPS, Geometry, Arithmetic, and Differential Equation of Period. And today we are pleased to have Gabriele Bogo from Technology University of Darmstadt, Germany. And if I want to say about his PhD, he did his PhD in CISA under supervision of Don Zaguirre and Fernando Rodriguez Villegas. And today he will talk about extended modularity and deformation of Riemann surfaces. Thank you, Gabriele. Go ahead, please.
Okay, thank you very much for the introduction and for having invited me to speak in this nice seminar. So I will speak about some functions on the upper plane that appears after perturbing a very classical differential equation related to the uniformization of Riemann surfaces. So let's first start with the classical theory of uniformization of zero puncture spheres. So we start with X, which is a puncture sphere with n punctures. And to such a Riemann surface, we always associate a polynomial whose roots are definite punctures, so not the one at infinity. And the classical theory associated to this Riemann surface a family of differential equations, second-order differential equation of this form, so-called Fuchsian differential equations, whose singularity are given precisely by the zeros of this polynomial, so from the punctures of the sphere. And you have some free parameters here called accessory parameters that are in principle n-2, but one will be fixed to have this value in order to preserve, to make infinity a regular singularity of the differential equation, but the other one are free. Let me explain you why you have these parameters. So for every choice of this row I, every solution at a singular point of this differential equation, at every single point, you have a holomorphic solution and a solution with a logarithmic singularity. And this analytic property is independent of the choice of parameters here. But of course, when you change parameters, you change the global behavior of the solution. So in particular, the local monodromies of the solution near the singular points does not determine the global monodromy of the differential equation, which is, for example, what happens for hypergeometric differential equation. This is not the case, and the global monodromy depends on the choice of these accessory parameters. And what we are going to do, at least the classical theory, is all about finding the correct value of the parameter given a puncture sphere. So more precisely, you pick two independent solutions of your differential equation, and you construct the ratio, which will be in general a multi-valued function on the surface, but then you can lift it to the universal covering to have a proper complex valued function, and this function eta tilde depends on the choice of the parameter, and this is why I put the subscript here. And this function in general will not be univalent injective, will have some bad behavior from the mapping point of view. But what Poincaré conceived at the beginning of this study of this differential equation is that there should be a choice of the accessory parameter, rho, such that this map, in fact, gives a biomorphism between the universal covering of the Riemann surface we started with and the apparent plane. And when you have such a biomorphism, then you can invert this map and construct a covering from the apparent plane to the surface. This was the classical idea by Poincaré. He then later abandoned this circle of ideas while proving the so-called uniformization theorem. But still, there is this problem, so-called accessory parameter problem. Given a Riemann surface, to find the value of the accessory parameters such that these functions constructed from the solution gives a biomorphism between the universal covering and the apparent plane. As I told you, then 20 years later, more or less, Poincaré and Koebe proved the so-called uniformization theorem that tells that every Riemann surface of this kind of the apparent plane has universal covering, and this in sort of indirect way proves also the existence of the accessory parameter and the particular choice, which is called the Fuchsian choice of the parameter, but it does not give any clue on how to find this parameter, and up to now there are no general proof for the existence of this parameter independent of the general proof of the uniformization theorem. And here I just wrote a list of different people who studied this problem in a sort of explicit way, wanting to determine the Fuchsian value of the parameter. And the only case where you have a real solution of the problem was given by Smirnov in 1910, where he proved that the accessory parameter exists for a sphere with 4 punctures and real punctures. And all the other cases here are more of numerical nature, trying to determine the accessory parameter using different techniques. When I try to do it, for example, I used modular forms in a way that you will maybe understand later, but I will not speak about this today. This is just to say that to find the accessory parameter is a hard problem. Many good people tried, that could not and didn't manage to do it. And as you can see, every time people tried in the easy cases. So when you have a low number of punctures and small genus. Okay. And how modular forms are related to accessory parameters uniformization? The point is that when you find such a map from the universal covering to the upper plane, then the monodromy group of your differential equation is precisely the deck group of transformation of the covering. And this group will be for sure a Fuchsian group, so a discrete cofinite group of SL2R with limit set the real line. We're just discussing the Fuchsian case. And in this case, when you have this group, you can speak of modular forms on this group. And what happens is the following, that your holomorphic solution, the holomorphic solution of your differential equation, is nothing but a modular form locally expressed in terms of a modular function. In the case we're studying today, which is the case of genus zero surfaces, this is more than a modular function. This is an out model, which means that this gives an isomorphism between the compactification of the Riemann surface and the upper plane with the cusps. So, but what you have to keep in mind is that the holomorphic solution of the differential equation is nothing but a modular form, or a root, more generally, of a modular form on the monodromy group. Today we will assume that we can do everything with a modular form of weight 1, so we will not care about the square root here. In general, you can always pick a modular form of weight 2 and then take the square root, but today we will assume that the modular form of weight 1 with this property exists, and it happens very often. This is only a minor restriction. Okay. Given solutions of the uniformizing differential equation, you can construct explicitly a co-expansion of your modular form using the so-called Robinus method for the determination of the solution of the uniformizing differential equation. What happens in the following? You take, you consider a Fuchsian singularity of the differential equation. For example, you can fix a puncture in 0 and take the singular point in 0. And then you can construct the solution, holomorphic solution, by a simple recursion, so-called Frobenius method, and the second solution, which is of form log of t times the holomorphic solution plus something else which is holomorphic, and you can also determine this coefficient using a different recursion related to the first one. At this point, you want to take the ratio of the solution, as I showed you before, but since we're working with power series, we prefer to take the exponential of this ratio in order to have a proper power series. And now this starts with Q, so with T, and we can invert it, so take the compositional inverse and express the exponential of the ratio of solutions in T, and then T as a function of this Q. And finally, you can substitute this series for T into the holomorphic solution in place of T and get another function of Q. What happens when you have the correct choice of the accessory parameter is the following. When the accessory parameter is correct, you know that the ratio is the Fuchsian one, you know that the ratio of solution will be coordinate on the upper plane. So what in general is written as tau in the upper plane. But then this exponential will just be the usual parameter at infinity you consider in the theory of modular forms times a non-zero complex constant. So there is some shifting. And then this makes this function t, which is a priori, in principle, is a function of dq, but then dq becomes a function of tau. This makes also this t a function of tau in this way. And this becomes your covering map, your Hauptmodul, so a modular function of a modular function. And the holomorphic solution, well, once you substitute t here and you choose the correct parameter, will also become a function of, on the upper plane, a function of tau, and this will be the holomorphic modular form of weight 1 that I discussed before.
Maybe, Gabriele, you assume that there is a holomorphic solution, or at t equals 0, you assume a kind of a specific Riemann scheme.
Yeah, but but it is a general property of the family of differential equation that I showed at the beginning. They also have 0 exponents at every singular point.
Okay.
At every finite singular point, you have a holomorphic solution, and a holomorphic solution times with times a log. This is a property of the family of differential equations. Yeah. In fact, they are constructed to have that property. In the classical theory, you just want that property, and then you try to find all possible differential equations with that property, and you find that they are family depending on n-3 parameters, the accessory parameters. Okay. So this was just to show you how to construct a modular form from the solution of the uniformizing differential equation. Okay. Now there is another explanation of why the accessory parameter problem is hard. Why it is hard to determine the accessory parameter? Well, it's written here. If you are able to determine the Fuchsian parameter given a surface, then you will be able to describe the co-expansion of modular forms on every Fuchsian group. You know, this is sort of impossible problem in general to give such an explicit expansion for every Fuchsian group. And this transcendence of the problem is precisely this difficulty. Okay, here I listed some cases where the study of modular forms related to uniformizing differential equation was relevant, and there is a nice problem about the algebraicity of accessory parameters, of the integrality or of the Taylor expansion of a solution. But maybe we can discuss this later after. Maybe, yeah. If you have questions, you can ask, of course, but I don't want to speak about this now. But this is sort of nice problem, quite subtle. Okay. What we're going to do today is not to study the Fuchsian value of the accessory parameter, but to study some deformation around it. So, as I showed before, from the holomorphic solution, substituting the power series for the Hauptmodul, depending on the parameter, we can consider a new Q-series whose coefficient depends on the choice of accessory parameter. And what we're going to do is precisely to study the derivatives of this function here with respect to the accessory parameters. What is written here? We just take this function, consider the n derivative with respect to accessory parameter, then specialize to the Fuchsian value. And after this specialization of the Fuchsian value, this Q is small q, so the usual parameter at infinity, and this makes this derivative a function on the upper plane. So then if you take a sort of Taylor expansion around the Fuchsian value of the accessory parameter, these are the functions of the coefficients, and these are functions defined holomorphic on the upper plane. And we know from what I said before that in the case m equal to 0, so the constant coefficient, let's say the coefficient corresponds to m equal to 0, would be the modular form of weight 1 we constructed before. And the question is, which function do we get for higher values of m? Yeah, this is what I will speak about today. Are there questions so far?
Maybe I have one question. So in this case, there is just one cusp, or there can be more cusps. In one cusp,
the cusps are in bijection with the punctures of the sphere. So you have if you have n punctures, then you will have n cusps for your group.
So you can do a Q expansion around any cusp, but not just one of them. This is
precisely. Okay. Yeah. For example, here we're doing it at infinity because we assumed without saying that our output model will map the cusp at infinity to 0. But you can find the solution around any singular point and then find the expansion of the modular form around the cusp, which is in bijection to that singular point with respect to via the modular function, via the output model. Okay. In the title of the talk, I wrote Deformation of Riemann surfaces, and I want to make this precise now. From the geometric point of view. Before to attack the problem that I presented, I want to just spend a few words about how to make rigorous the connection with the deformation of Riemann surfaces. And the correct way to do is to speak about theory space. So I just make this digression for 5 minutes and then come back to the original problem. But I want to show that deforming the differential equation and taking these derivatives here is precisely to deform the surface, as is done in Tensor theory. So just a reminder of what happens in Tensor theory. We start in this case with a Fuchsian group, so with the surface, with the quotient, and we consider a family of functions associated to this Fuchsian group. This function, I don't know, they might know, are measurable functions. They are complex valued, and they have this transformation behavior with respect to the usual action of the Fuchsian group on the upper half plane. So the Beltrami differential because they behave like a 1-1 differential. We denote by B of gamma the space of such measurable functions, and then we want to consider the smaller space of such functions with subnormal smaller than 1. Okay, if you do like this, then we can define a differential equation on the complex plane, just extending this to the complex plane by symmetry. We define a differential equation like this. So z, the derivative with respect to z, it's a complex number of a function, is equal to mu of z times the derivative with respect to z bar. This is called the Beltrami differential equation. And if mu is, as I wrote above, with the special property on the norm, then there exists a unique solution after normalization of this Beltrami differential equation, which restricts to homeomorphism of the upper half plane. So you start with a measurable function with this property, you solve this differential equation, and you end up with a homeomorphism of the upper half plane. Then, if you conjugate the Fuchsian group you started with respect to this homeomorphic solution, you get a group which is again Fuchsian. This is very important. And then you do this for every possible measurable function mu with this property, and for every mu you construct this group conjugating by the homeomorphic solution to the Beltrami equation, and you call the space of equivalence classes of representation constructed in this way the Tensor space of the Fuchsian group gamma. Okay. So in particular, we get a map from the space of Beltrami differentials of bounded norm to the Tensor space, sending M to the representation defined by mu to the representation defined by mu. And this is not only a map, this is holomorphic, and in fact, you can define a complex structure here using the fact that this map, by requiring that this map is holomorphic. Why do we care about this? Because of the following reasons. This space is a manifold, and the coordinates are given by this map locally, and the cotangent space to the Tensor space, for example, in this point here, is given by the so-called space of quadratic differential that are simply the cusp forms of weight 4 with respect to the group gamma. And conversely, then there is for every quadratic differential, there is a possibility to construct a Beltrami differential, just sending a cusp form of weight 4 or quadratic differential to this function here. So it's conjugate times the imaginary part of tau squared. And you can produce from a cusp form of weight 4 a Beltrami differential, which in turn give a point in the Tech-Miller space. The problem is that the Beltrami differential you get at this point is not small enough, so the subnorm is not bounded by 1 in general. But you can make it smaller, as I will show in the next slide. And now we're connecting to the previous theory that I explained. So you have this space of quadratic differentials, which is the space of cusp form weight 4. And there is an isomorphism between this space and certain space of rational function on the surface X, where X is again a bit of same mod gamma. And you can construct cusp form from a rational function of this form using this linear isomorphism. Then from this cusp form of weight 4, you can construct a Beltrami differential using the map that I showed before. This is not small enough, but you can take a real number, small, such that this Xi multiplied by the Beltrami differential constructed from the cusp form is of bounded norm 1. And then construct the Beltrami differential equation and take a homeomorphic solution. So let me repeat once again. What we did was just to construct a cusp form from a rational function. The rational function is given by t to the I divided by the polynomial, which is the one that gives the punctures on the sphere. From this cusp form, we constructed a Beltrami differential, and we multiplied it by some small constant in order to have subnorm smaller than 1. Then this gives us a homeomorphic solution of the Beltrami differential equation, and in particular we get this commuting diagram. This is the surface we started with. This is the surface we get quotienting the upper plane by the new group that we got conjugating the first one with the solution of the Beltrami differential. And we have this map here, and we have the homeomorphism given by the Beltrami differential equation on the upper plane. We have a Haupt model here and another Haupt model here. Now, if we let everything depend on the value of Xi, of this real number, we think of it as a real variable, we have that this function is holomorphic in this, and the solution of the Beltrami equation and this new Haupt model are not holomorphic, but they are real analytic in this variable here. But it is enough for our purposes because what we want is to differentiate this Haupt model with respect to Xi, and the final result is precisely that. What we want to do, I explained before, the derivation from the differential equation is precisely the derivation with respect to this parameter in Tech-Miller theory. And this is the connection between the deformation theory of Riemann surfaces and our operation from the accessory parameter of the uniformizing differential equation. And this is only true for modular functions, because in Tech-Miller theory we can do only for modular function or for modular forms. What we will do later is a sort of extension of this if you want. And the first hint of what we may do just performing this operation is given by the following lemma by Halfors, which tells you essentially that this derivative here is just t prime multiplied by an Eichler integral of cusp form of weight 4. So here we see the first connection between this operation and Eichler integral, but that will be more clear in the following slide when I will speak about this operation without referring to Tech-Miller theory. Okay, here the digression is finished. Do you have questions about this part or other questions?
You told that the second t power psi nu I is not holomorphic, yeah?
This is holomorphic function on the upper plane, but it is real analytic if you think this as a function of this psi here.
Mm.
In fact, we are computing this derivative with respect to psi bar. Yeah, but it is an holomorphic function on the upper plane. It is an Haupt model as t is. It's simply on a different group.
But if it is holomorphic, then You are this derivation with respect to psi bar.
Yeah.
Okay.
Yeah, maybe I can show it again. This is function from the floor plane, and it is holomorphic as a covering map here. But to construct this one, we solve the Abel-Tami differential equation, and some value here is involved. And if you consider this as a function of this one, this is reanalytic. But this is holomorphic in tau, in the usual variable.
Okay, thank you.
Okay, thank you. So let me move on to the actual study of the formation of accessory parameters. So this is the first result. We are in the situation that I explained at the beginning. We have a puncture sphere with n punctures. So gamma is a group of genus 0 with n cusps. And we have a holomorphic solution to the uniformizing differential equation, the differential equation I showed at the beginning. And the first result is the following. If you consider the derivatives with respect to the accessory parameter of the solution of the differential equation, which is not the modular form, but is sort of first step. If you compute the derivatives of the holomorphic solution with respect to the accessory parameters, then this function satisfies again a Fuchsian differential equation, but higher order of order 2 times j plus 1 if you compute the jth derivative with respect to the accessory parameter rho I. And then the monodromy representation of this new, associated to this, the solution of this new differential equation, which is a value in GL of 2, this is should be j plus 1, not n. So the solution of the monodromy of this representation of this new differential equation is simply the iterated extension of the representation of the uniformizing differential equation. As I told you at the beginning, if you choose the correct value of the accessory parameter, then the monodromy representation gives a Fuchsian group, which means that you have a representation of the fundamental group into SL2R, and the image is a Fuchsian group. The monodromy of the differential equation solved by this derivative is an iterated extension of this representation here. And I want briefly to discuss the proof, if there are no questions on the statement. So I want to give some detail of the proof because it's a sort of general argument that works in this case, so maybe it's good for you to see it in detail. What we do is
just to remember that this y was associated to a weight one modular form, yeah?
Yeah, when you substitute the Fuchsian value of the accessory parameter, this is locally is simply the
f that you
f of tau, yeah.
Yeah.
For
so
locally,
the j's derivation will be a modular form of weight 2j plus 1. So okay.
Yeah, but now what you mean is the derivation given by d of the tau.
Yeah.
But we are not considering this one. We are considering f is some bigger f of q specialized when you specialize rho to the Fuchsian value. And what we're going to compute is the so-called rho delta rho of f, which is the derivative with respect to rho of this function here. And then specialize. This is the deformation. And to understand this, we first understand what happens at the level of the holomorphic solution of the uniformizing differential equation. And then we will lift this one to this one. That will be the second step.
Okay.
So in particular, this one will not be a modular form or a quasi-modular form, will be something different.
Okay, thanks.
Okay. Let me just give an idea of the proof. So what we do is to consider the so-called deformation of the differential operator. This is this part is the differential operator we started with, associated to our punctured sphere, but we are adding this new formal parameter epsilon I, only up to n minus 4, in order to preserve the fact that at infinity you have a regular singularity. And to search differential equation, you always can associate a linear homogeneous recursion. In the case, for example, I put here the example of a 4-punctured sphere. We have this kind of recursion that lets you construct the holomorphic solution. And so again, I wrote here, you now consider a solution of the linear recursion will be something with heavy notation because it depends on many things. So this solution of the recursion, so the generative function of this with respect to t will give a solution of the differential equation, can be written in this way. So as something expanded in the formal parameters we added, and the coefficient will be some function of rho. And out of this solution of the recursion, you construct 2-power series. The first one is just the generating function of, you fix one index here, which is fixed here, and then construct the generating series with respect to powers of t. And the second one, you just sum over every possible indices. And so this one is what we are using now. You can compute, this depends on rho and on epsilon, and if the derivative with respect to rho I is the same as respect to epsilon I. And the proof of this fact is simple, just depends on the fact that the linear recursion that you use to define the coefficient of this function in this linear recursion, rho and epsilon play the same role. So this is why this is true, but this is an important consequence for us. So the j derivative of the homomorphic solution with respect to the accessory parameter rho I will be, by definition, the j derivative with respect to I of d phi 0 we constructed before, and will be in particular this function. So associated to the index 0, 0, j in the ith place, and then 0 again. And what I want to stress now is that we started with something with indices 0, and on the 8th place, the index is raised to j. So what the derivation with respect to the accessory parameter is doing on our holomorphic solution is sort of raising the index in this way. On the other hand, we have also the action of the differential operator L epsilon on this function phi that I defined before, and you can prove that it acts in this way. And what it does with the function for a given index is to lower the index by 1 each time you apply it, and then multiply it by some power of t. So as I put in evidence here, the derivative with respect to the accessory parameter is lowering the indices, is raising the indices, while the action of the differential operator L is lowering the indices and multiplying by some power of t. So the idea is to balance these two actions. So if you want to understand how this, what is this doing to the holomorphic solution, we want to balance it applying many times as needed the action of the differential operator, but we have some power of t that appears here, we don't like. So what we do is to introduce new differential operators for each k with this property. They are Fuchsian, they are defined by this property. So Lk of t to the k times y is precisely L applied to y times t to the k plus 1. And the action of these operators on the general power series that I showed before, multiplied by a power of t, acts like the operator that I defined before. And you see again, when you fix the index, this is just lowering the indices and multiplying by a certain power of t. And I don't want to say everything in detail, but combining everything together, you have that when you apply L to this function here, that is precisely the derivative of the holomorphic solution with respect to rho I dot j. When you apply L, you get this one with the index here lowered by 1 times t to the I. And then you can apply the operator of index I again, and you will get something which is lowering again the index but multiplying by a higher power. And so combining the action of all the operators we defined before in a finite number of steps, we'll be able to click this function here, which is precisely the function we're interested in. And since all these operators are operators of order 2, this shows that this function is annihilated by some differential operator of order 2 times j plus 1. And this function here, as I wrote here, is precisely the one we are studying. So this is more or less the argument of the proof. And in this slide, I wrote a lot about monodromy, but the basic idea is that every one of the operators Lk that I introduced before, again, has modular solutions. And the reason is why that the operator we started with has modular solution, f and tau f. This gives a basis of solution on the upper half plane. This one, remember, is such that Lk of tk of y is tk plus 1, or tk L of y. And so in particular, when you put t to the k times f here, you will have f here, and this is 0, so this will be 0. So a basis of solution of this Lk is given by t to the k times f and tau t to the k times f. And in particular, this is a modular form of weight, the same weight of f. Probably will be not holomorphic, but this is not a problem. This is just to say that these differential operators, again, are Fuchsian and have modular forms as solution. And this precisely means that the monodromy group is again the same as before, this gamma. And then when you compose together differential operators, the monodromy will always be extensions of the single monodromy representations. And so in this case, it will be an extension of this representation pi to gamma. Okay, this is the first step in understanding the derivation with respect to the accessory parameters, and then we lift everything to the upper half plane. So recall what we did before. We have our solution, uniformizing differential equation, a solution, and from the solution we can construct a power series that then we specialize to the out module, and another power series then we specialize to the modular form of weight 1. And as I stated before, we are interested in computing the derivatives with respect to the accessory parameter of this function that we construct before. Again, when we specialize this function here for rho equal rho f, we get a modular form of weight 1. Now we want to compute first the derivatives with respect to the accessory parameter and then specialize. And we want to see which kind of function we get here. Instead of doing this only for the function f coming from the uniformization, we want to do it for every modular form. And the way to do this is just to define this deformation operator for f. This f is the one coming from the differential equation. For t is the out module coming from the differential operator. And now, since f is of weight 1 by assumption, every modular form of weight k can be written as f to the k times a rational function of t. And then we can define the deformation operator on G, on a general modular form, as the deformation operator applied to fk times RT, intended as a derivation. So what we did is was just to define this operator in terms of accessory parameter when possible, so to function coming from the uniformizing differential equation, and then exploit the fact that every modular form can be written in this way to extend the definition of the deformation operator to every modular form. And this has advantage that now we can try to describe this derivation in terms of known derivation on modular form and quasi-modular forms. And this is what we are going to do. But before to give the main theorem, let me recall something about derivations on modular and quasi-modular forms. So quasi-modular forms are a function of this form here, a holomorphic function on the upper half plane, which has some weaker, a relaxed transformation property with respect to the action of the group gamma on the upper half plane. They transform in this way. So if G were a modular form, you will forget about these terms here and just have a modular form G0 here. Quasimodular is something that transforms like a polynomial in C over C tau plus D with modular coefficients. And from a certain point of view, this space is better behaved than the space of modular forms. For example, you can define 3 derivations on this space: the usual differentiation, the weight operator, just take a quasimodular form and multiply it by its weight, and then you have the so-called delta operator, and the delta operator can be defined in terms of this transformation property. You just send G0 to the coefficient G1 in this expansion here. An important property of these 3 derivations is the way they behave with respect to each other, and they satisfy these commutator relations, which means that they give to the space of quasimodular form a Accessory structure. And finally, but we're not going to use it today, I think, quasimodular forms can be written uniquely as polynomials in a certain quasimodular form of weight 2, which is non-modular. In the case of Accessory, it's called Eisenstein series of weight 2 times with modular coefficients. Okay, please keep in mind these derivations, because now we're going to see them in the main result. So this is the answer to the question I asked at the beginning. Which behavior have the higher terms in the expansion of the solution of the differential equation in terms of derivation on the accessory parameters? So we have a puncture sphere as before. We have a modular form on the uniformizing group. And then the result is that there exists a basis of the space of cusp form of weight 4, which is of dimension n-3, which is precisely the number of accessory parameters. There exists a basis of the space such that the derivation with respect the deformation operator applied to the modular form G, which is defined in terms of accessory parameter as I shown in the previous slide, is simply given by a combination of the first Rankin-Cohen bracket on the space of quasimodular form of the deformation of G of order smaller than J, and the deformation of certain Eichler integrals. So for a given HI here and cusp form of weight 4, we define HI tilde as this Eichler integral. So just sort of integrating 3 times with respect to tau. And you apply the deformation operator also to these Eichler integrals, and they are given by this formula again, integrating some Rankin-Cohen brackets. But to understand the statement, please look at the examples here. So in the first case, the first deformation of a modular form is just the first Rankin-Cohen bracket of G with respect to the Eichler integral of a cusp form of weight 4 associated to the given index of the accessory parameter. So every accessory parameter will give a cusp form of weight 4, and the deformation with respect to that accessory parameter will be just the Rankin-Cohen bracket of G with respect to the Eichler integral of that cusp form.
Sorry, what is this derivation without index?
You mean this grid here?
No, this partial power k. In the first Rankin-Cohen bracket that you wrote.
Here?
Yeah, exactly. This
part. No, I'm sorry, I simply forgot to write it. It's the same one. Yeah. This is just to say that this deformation operator is well behaved with respect to Rankin-Cohen brackets. It takes like a derivation with respect to them.
And in the example, it is which Rankin-Cohen bracket? The first?
The first one. It's always the first one. But you can have nested Rankin-Cohen brackets. So the first deformation of a modular form is given by the Rankin-Cohen bracket of G and the Eichler integral. The second one is given by the first one, which is this Rankin-Cohen bracket. Again, a Rankin-Cohen bracket with the same Eichler integral. So you can write, if you want, this one using higher Rankin-Cohen brackets. If you want it, I don't know if it is useful. But you have to add something, which is G and the 3 times iterated integral of the Rankin-Cohen bracket of h, I, and its Eichler integral. So let me notice that h is of weight 4, the Eichler integral is of weight -2, the Rankin-Cohen bracket, the weight of the Rankin-Cohen bracket is 4 minus 2 plus 2. So again, this is of weight 4. And we are always integrating something of weight 4 3 times. So this is consistent with what we do in general with modular forms. And so actually each time we apply this deformation operator, we have to add new deformation, which is precisely given by the integration of a Rankin-Cohen bracket of a cusp form with respect to an Eichler integral in this case, or more complicated function later. And we have also an extension to quasi-modular forms. I didn't write it to the full formula here, but in this case, G is a quasi-modular form, for example, of depth at most 1. You have to care about the depth. And so this is the delta operator on quasi-modular forms, and the formula is of this form here. You have the usual Rankin-Cohen bracket, but you have to add the second derivative of the Eichler integral and the delta operator applied to G. Okay, other questions about the statement or this result in general?
Maybe one question
Yeah.
I forgot. If you integrate this Eichler integral of modular form, is still a modular form?
So in general, the Eichler integral, for example, no, if you have, as in this case, a cusp form, then you have the Eichler integral, which is defined in this way.
Yeah.
Then if you consider the slash operator in weight -2, if it were a modular form, it would be something like this, but it's not something like this. You have to add a polynomial, which depends on the matrix gamma. This polynomial is of degree 2 in this case.
Anyway, the conclusion is that the transcendental degree of all of the field generated by all these functions is growing, no? Because when you are integrating more and more, and then new functions are coming, and so it's not like algebra of modular form which is finitely generated. Okay.
In fact, this is an example. The fact that integration is very different from derivation in the case of modular forms, right? So we always have to add some new generator. The point is that in some sense we can control it because we know that we can express it in sort of familiar way, just using modular forms, Eichler integrals, Rankin-Cohen brackets, and then integrate it the right number of times with respect to the weight. So this is more or less the idea. And I don't want to give the full proof of the result, but just to show you how Eichler integrals naturally appear from the differential equation point of view. So if there are no more questions, I will go to the proof. I will just prove this first derivations, the formation for the modular form coming from the differential equation. So this is this F, remember, is just T composed with T of Q. Okay, this is just a holomorphic solution of the differential equation. Okay, just by definition, what is the derivative here is this one. And you of course, using the usual rules, you split it into the derivation of the holomorphic solution with respect to the accessory parameter and the derivation of this function T with respect to the accessory parameter. This one is the one that we studied before in the general case. And the fact that this satisfies a differential equation of order 4, as I wrote here, means that we can write it using integration and the solution of the first one. Since we know this differential operator, we know that this is a solution of a composition of differential operators. This makes possible to write this solution as the solution y we had at the beginning and integration. And this is the formula you get. Okay? It seems something complicated, but then now we go to the upper plane. But this is just the integral of t to the I times y divided by y squared times p, where p is the polynomial given the puncture of the sphere. We integrate again and multiply by the holomorphic solution. Now, we want just to evaluate this integral on the upper half plane using this relation between the function, the variable on the Riemann surface and on the universal covering. And then this simply becomes the integral of some function hi, where hi is f to the power 4 times t to the I times the polynomial t, the one giving the punctures of the sphere, integrated 2 times. And what you can prove? You can prove that this is a cusp form of weight 4. This is not hard, but it requires some work. But then you have 2 times the integrated integral of cusp form of weight 4, which is precisely the first derivative of its Eichel integral. Okay, and then multiplied by the function f, which is the lifting of the holomorphic solution. So this is why you find Eichel integrals in the of cusp form of weight 4. And if you try to evaluate the second part of the formula, you have this derivative here. And again, you do more or less the same stuff. It's a bit slightly more involved, but really nothing serious. And then you have basically to integrate what you integrated before once more, and then you get your Eichel integral again. So you see that these integrals of cusp form weight 4 appears very naturally from the point of view of the differential equation. And then with this, you can build the complete proof of the theorem. And here I just remark that the Eichel integrals are obtained as the derivative with respect to rho of this function here, y2 over y, where these are linear independent solution of the uniformizing differential equation. And this gives the coordinate on the upper half plane. So the Eichel integral should be thought as the deformation of the coordinate tau on the upper half plane along the direction given by the accessory parameter rho I. Okay, now we're coming to the end of this presentation, and I want to give an alternative description of this derivative induced by derivation in the accessory parameters in terms of vector valued modular forms for specific representations. And this representation has the following one. So you take the symmetric S power of 2 copy of C, and call this space P of S. And then you have an irreducible representation of SL2R that you can restrict to a Fuchsian group. And this is called the symmetric tensor representation of dimension S plus 1 of the Fuchsian group gamma. And here I give a few examples on a given basis. So in the case of 0, you just get 1. Sim 1 is just your matrix gamma you started with. And sim 2 has this form, for example. And you can consider the space of vector valued modular forms with respect to this representation. So they are functions, vector valued functions that transform in a modular way with respect to automorphic vector given by these representations. And these representations here are relevant in the theory of classical modular forms because of this reason. This relation proven first by Kuhn and Shimura and then by Choi Lee recently. The space of vector valued modular forms with respect to this symmetric tensor representation is precisely the space of quasimodular forms. And you can be more precise just given the weight and the dimension of representation are related to the weight and to the depth of the quasimodular form. So in a sense, studying vector value modular forms with respect to this representation is like studying quasimodular forms in a way. Okay, how this relates to what I explained to now. So the first theorem I proved was that the derivative of the homomorphic function with respect to the accessory parameter satisfied higher order differential equation. And then the monodromy of that differential equation is just a iterated extension of the monodromy of the uniformizing differential equation. This means that this function here, so the lifting to the upper half plane of this derivative, is a vector value modular form with respect to that monodromy matrix, which is this in this case. That has a very special form. If you consider the period polynomial of the Eichel integral, so you take the Eichel integral, as I wrote before, this is not a modular form, but you you take the slash operator in weight -2 with respect to gamma -1, you get a polynomial. It's called the period polynomial in certain cases, which in this case, since h is of weight 4, is a polynomial of degree 2 with coefficient. It depends on the matrix, on the element gamma of the Fuchsian group. And then out of this polynomial, you can construct this 2 by 2 matrix. And this 2 by 2 matrix is precisely the one that gives you the extension of the symmetric tensor representation with respect to this is the vector value modular form. Similarly, you can do it in every case. I wrote here another example. When you consider the second derivative, then you will have one extension, one first extension, and the second one. And again, you take the period polynomial of the cusp form, h, and you construct the first extension, the one that I showed before. Now you have to construct another one, and this is still made by block matrices. Here you have the same block you had in the previous case, and here you have a new one where the matrix is constructed precisely as in the previous slide, but the coefficients are not given by the period polynomial of P, but by some second order polynomial coming from the transformation formula of this more complicated function here, which is not a cocycle in particular, but still you can construct this extension of symmetric tensor representation and get this vector value modular form. This follows from the first theorem, but it is not so important. What is more important is that also the function, the deformation of modular forms given by Rankin-Cohen brackets are vector valued modular forms. And there is vector value modular form with respect to extensions of differential of symmetric tensor representation, but in a different way. For example, before we had this kind of extension here, just gamma, gamma, and a 2 by 2 matrix here. In this case, we have sim2 here, sim0 here, and something here, which is given by the same coefficient of the period polynomial of the cusp form hi. And this rho I is a component of a vector value modular form in this way. But this means in particular that given some modular form here, we can construct in a well-defined way a vector value modular form with respect to some extension. But we can also consider this F as a component of a vector value modular form thanks to the Choyari and Quasimodular theorem. And this means precisely that the deformation operator that I defined from the differential equation in terms of accessory parameters induces a map of vector valued modular forms. So from the space here of vector valued modular forms of weight k with respect to is plus 1 dimension representation gives something, gives a weight k modular form with respect to an extension of symmetric tensor representation, and the dimension of this, the dimension of this symmetric tensor representation depends on the dimension of this one in this way. And so you can interpret everything, just forgetting about your differential equation, but in terms of some operators, maps between spaces of vector value modular forms from symmetric tensor representation to extension of symmetric tensor representations. So this is what I wanted to do to tell you for today. So thank you very much for the attention, and yeah, if there are some questions, I'm happy to answer.
Thank you, Gabriele. That's nice.
Thank you.
Any question?
Maybe Gabriele, do you know which is it? Let me formulate in this way: is it possible to classify this differential equation whose monodromic group are arithmetic? Because I think at the end, if you want to do a kind of number theory, then you have to restrict. So it's just Fuchsian among this the Fuchsian that you discuss. Do you know some of them which are arithmetic also?
Yeah, it happens in some cases, and maybe let me go to the beginning so that I can tell you something more. In general, it's something hard to determine from the differential equation. So the problem, given this differential equation, to find because in principle it's not even clear when this surface is uniformized by an arithmetic group.
I see.
There is no way to recognize the arithmetic nature of the uniformizing group from this from such a surface. So in some cases it happens. It is, for example, there is a paper by Zagier when it searches for differential equation whose solutions are given by power series with integer coefficients.
Yeah, exactly.
And it turns out that the differential equation has precisely uniformizing differential equation for sphere with 4 punctures. But if you look at the surfaces, there is no way to distinguish them among the other ones. So there is no. I think it's very hard in principle to do that.
I think even to recognize which one is Picard-Fuchs would be hard, I think.
Yeah. But this is related to the problem that I wrote here, right? So in the history, several times accessory parameters and differential equation were related to number theory in different ways. One of the most famous is the Bogo's interpretation of the Apellis proof of the rationality of Z of 2, Z of 3 in terms of modular forms, solving differential equations. But you can, in general, ask a different question, which is the one asked by Thomson, the group theorist, and then studied again by Chudnovsky and by Martin Müller and Müller-Zagier. And the question is the following. It's very subtle. You start with a sphere with punctures, but now you suppose that every AI is a rational number, or maybe an algebraic number. Then this gives you a set of accessory parameters giving the uniformization. And you ask if rho I are again algebraic numbers. And this is a very hard question. And the first who thought about this was, again, John Thomson, the group theorist, and motivated by Bailey theorem. And what he thought was that this is always the case. But it soon was verified that this is not true. So then someone else studied this problem, was the Chudnovsky brothers, that they were very good in computing numerically to use computers in number theory, and then computed such uniformizing differential equation for spheres with algebraic punctures. And their conjecture were that the accessory parameters are also algebraic or integral, only if the group uniformizing the surface is a subgroup of a triangle group, okay? Because you know that groups are arithmetic well behaved. But again, this is not true, because it was discovering, I think in 2011, a differential equation. It's called Moller differential equation, which is a uniformizing differential equation for a very special curve, a so-called Teichmüller curve, and which is called W17, is uniformized by a group, which is now, I think, gamma of W17, and this group here is not commensurable with any subgroup of a triangle group. Okay, so it has nothing to do with the conjecture with the group that Chudnovsky brother conjecture to be of arithmetic relevance in this type of differential equation. But still, the solution of the differential equation associated to this surface has integral coefficients, and the accessory parameters are algebraic integers. So you see, each time we are sort of enlarging the class of groups with arithmetic properties, and the group here is not commensurable to a triangle subgroup, but as a so-called modular embedding. So it embeds naturally in an arithmetic group acting on certain number of copies of the apparent plane. So you see that it is not even clear which groups are of arithmetic interest in this kind of problems. But it is a very fascinating problem and very hard, and there is no general idea of how it should go. It's very hard. Yeah.
Okay. Thanks. Maybe I stop recording and then we go to Testament.